right, let's look at another example. This is example 4 from the PowerPoint. So in this case, we have a drug that is a weak acid with a pKa of 5.5, and we've administered it, presumably per os, and it reaches the duodenum where the pH is 6.5. And the question is, between the duodenal pH of 6.5 and the blood plasma pH of 7.5, we'll just go with that today, where is this drug going to go? Is it going to want to absorb into the bloodstream, or is it going to want to stay in the duodenal lumen? Based on, again, we're just going to exclusively look at the ionization, knowing that in real life there's going to be other factors involved. So this is a weak acid. So again, if we go back to the basics, we know that in an acidic pH, this weak acid is going to be predominantly non-ionized. And in an alkaline pH, this weak acid is going to be predominantly ionized. And the pH at which the N equals the I is the pKa, in this case 5.5. So when the pH is below 5.5, it'll be relatively non-ionized. When the pH is above 5.5, it'll be relatively ionized. But, we're looking at two compartments whose pHs are both higher than the pKa. So our duodenum pH 6.5 and our blood pH 7.5. So now the basic idea of it moving from like an acidic environment to unlike alkaline environment isn't quite as clear cut. In this case now we're talking about pHs that are both alkaline relative to our pKa. So if we do this our mathematical way, then we've got 10 to the pKa 5.5 minus 6.5, and this is an acid, the N is high, so N over I. So we're going to have 10 to the negative 1 equals N over I. And again, the way that I've given that is what you would get in a calculator if you entered it, 0.1 over 1. And other people might be used to writing it as 1 over 10. Either way, just remember that the numerator here is the non-ionized and the denominator is the ionized. Likewise, on this side of the equation, we have our pKa 5.5 minus a pH of 7.5 equals N over I. So 10 to the minus 2 is N over I. And again, 0.01 over 1, or you may be used to writing 1 over 100. And again, I hope you can see that these are equivalent fractions. The relationship between N's and I's is the same regardless of which way you write this. So again, we're comparing two compartments. So we know that's how they're going to behave. That's how this weak acid will behave in either one of these. But on the blood side, again, our non-ionized and ionized are in this relationship. And we know now that ultimately if we're ever going to compare two compartments, we're going to want the N's to be equal to each other to represent equilibration. And so this is where just picking the 1 over 100, for every one N, there's 100 I's on this side of the membrane. If you did go with the 0.01 to 1, we know 0.01 over 1 is N over I. We need to know if the N is 1, what does that I equal? And that's going to be, we can cross multiply, or we can multiply top and bottom by 100. Either way, we're going to get 1 over 100. So we get to the same end place, regardless of which way we approach it. Now on this other side, we have, let me just clear this here. Again, our N's and I's have reached an equilibrium. On this side, for every one N, we have 10 I. And so getting to this point, if you're not clear on why we make N equal 1, come and chat with me. It's basically that we're simulating the point at which the N's have reached equilibrium. If you're not clear how we got to the 1 to 10 or 1 to 100, come see me. That's really just a matter of keeping your ratios matched. Once we have this, now we can say this is the equilibrium state, and however much drug we threw into this compartment, once it reaches equilibrium, there's going to be 10 parts ionized on the duodenal side, 1 part non-ionized on the duodenal side, 100 parts ionized on the blood side, and 1 part non-ionized on the blood side. So we basically add these 4 things up. So our 10 plus 1 plus 100 plus 1, we get 112. So there's 112 total states, total ways this could be. And again, of those, we could figure out any proportion. But what we care about at this point now is what's the total amount that's in this duodenum? What's the total amount that's in this blood? So we're basically going to add up the N's and I's on the duodenal side, which is 11 particles out of a total of 112. And on the blood side, 101 particles out of a total of 112. Now, we can take this a step further. This is what, if I ask you a question on the exam, it will be very much like the one, or on the quiz, very much like the one in the PowerPoint, which is, what percentage of drug is in this compartment. So for this example, if we say what percentage is in the duodenum once we've reached equilibrium, well, it's 11 out of 112. And now, because we're talking particles and particles, we're not trying to keep N's and I's separate, we can just do 11 divided by 112, which is going to give us roughly 10%. And likewise, what percent is going to be in the blood when equilibrium has been reached? It'll be 101 out of a total of 112. So about 90%. So what we've really just said is that if we drop this drug into this scenario, about 10% of it at equilibrium will be in the pH 6.5 compartment, about 90% will be here. Now, does that follow our basic rules? If we now are saying, relatively speaking, the duodenum is more alkaline and the plasma, is more acidic and the plasma is more alkaline, just relative to each other. They're both more alkaline than the pK of this drug, but what we know is that at this 6.5 pH is going to be more ionized than non-ionized, but at the 7.5 pH it's going to be way more ionized. So relatively, you can see that even if we're ionized in both states, there's still going to be a net movement, this being a weak acid, from the acidic pH, the lower pH, toward the higher pH, where it's just going to be more ion trapped. And that's exactly what we see with 10% and 90%. Now, these are percentages. And if we take a certain amount, let's say we give 300 milligrams. So instead of just saying some arbitrary, 100% of drug, if we give 300 milligrams, then what we're saying is 10% of it, so approximately 30 milligrams of drug, would still be in the duodenal lumen at equilibrium. And 90%, so about 270 milligrams of the drug, is going to be in the blood. So again, the clinical question we may ask is, will this drug absorb well from the duodenal lumen? Well, yes. If all other things are considered equal, this drug will move from the lumen into the plasma and then be trapped and stay there.